Hello and welcome to another video for Calculus 1. In this video, we are going to discuss about another application of derivatives, which is called L'Hopital's rule. So we learned how to find limit in chapter 2 before we started derivative, and then we use limit to define derivative, and we did so much on derivative. Now what we are going to do is we are going to use the derivative actually to find the limit for some special cases. So when we are asked to find the limit of a rational function, usually when we have this f of x over g of x and we are finding the limit, we might end up with 0 over 0. So we might get 0 over 0, or we might get infinity over infinity, okay? So when we did that in the limit chapter, we tried to factor out, okay, and then cancel things and avoid that 0 in the denominator. But sometimes it is unavoidable. We really cannot factor out, we really cannot simplify, and we still get 0 over 0 or infinity over infinity. So if we get something like that, when we just do the direct substitution, we call that type of limit or that type of form is called the indeterminate form. Okay, we really cannot evaluate that. That's not valid mathematics. So now how to figure out the limit, or how do we know if even if the limit exists or not? Okay, so there's something called a rule. There's a rule where we use the derivative to find the limit, so which is called the L'Hopital's rule. What basically this does is if we get indeterminate form of 0 over 0 or infinity over infinity when we do direct substitution, we're evaluating limit. What we can do is we can find the derivative of the numerator and the derivative of denominator and try to do the substitution. And the limit that we obtain from here is exactly same to the limit of this function here, okay? So again, one thing that we should not be, two things here that we really need to pay attention is we can use this rule only if we get 0 over 0 or infinity over infinity. We cannot use this rule if we have a number over 0, okay? Or a 0 over number is just 0. But if we have a number over 0, we really cannot use this rule. This rule can be used only if we have 0 over 0 or infinity over infinity. The first thing. The second thing here is when we are finding derivative here, we are finding the derivative of numerator and denominator separately. It's not a quotient rule here, okay? So just find the derivative of the function in the numerator or the expression in the numerator and the derivative of the expression in the denominator separately, okay? And then this limit, rule is valid for either two-sided limit or one-sided limit or infinite limit, limits at infinity. So it is true for those cases as well. And again, the note here I am just going to repeat that. We can use this one only if we have 0 over 0 or infinity over infinity. So let's look at some examples. The first one, so let's do the direct substitution and check. So if I plug in 3 here, I get 3 cubed minus 27, so which is 0 in the numerator, sorry. So 3 cubed is 27, so 27 minus 27, 0 in the numerator, divided by, if I plug in 3 here, again I get 0 in the denominator. So this is 0 over 0 form, and it's very important that we denote this one so that we know that we are going to use the L'Hopital's rule, okay? So we have 0 over 0, that means we can use the L'Hopital's rule. So let's go ahead and use it. So limit as x approaches 3. So what we do is we find the derivative of the numerator. So we get 3x squared minus 0, so it's just 3x squared, divided by the derivative of the denominator is 4x cubed plus 4. Now if we do the direct substitution, we are not going to get 0 over 0. Okay, so if I plug in 3 in the numerator, I get 27, because it is 3 times 3 squared, which is 27. And if I put 3 in the denominator, so 3 cubed times 4 plus 4, this gives us 112. So that is our limit. Okay, let's look at the next one. Now again, if I plug in 1, so I get 1 squared minus 1, which is 0 in the numerator, divided by, if I plug in 1, this becomes sine pi times 1 is sine pi, and sine pi is 0. So this is also of the form 0 over 0. Okay. Now let's use the L'Hopital's rule. So we'll have limit x approaches 1, derivative of the numerator is 2x divided by, so the derivative of sine ax is just a cosine ax. So you might be wondering, how do we get that? Just using the chain rule. So finding the derivative of sine constant times x is, derivative of sine is cosine ax, and then finding the derivative of a times x is just a. So we bring that a right here, okay? So in general, if we have sine ax, the derivative is a cosine ax. So the derivative of this function is pi cosine pi times x. Now if I plug in 1, again, I'm not going to get 0 over 0. I will get a finite number. So when I plug in 1 in the numerator, I get 2. And then pi times cosine pi times 1 is cosine pi is negative 1, so I get negative pi in the denominator. So the limit is negative 2 over pi, which is a finite number. Let's look at another example. Now if I plug in 8, I get, in the numerator, I get 8 plus 1, 9, square root of 9 is 3, minus 3 is 0. Similarly, if we plug in 8 in the denominator, so 8 is squared 64 minus 7 times 8 is 56, minus 8 is, we get negative 64 here and positive 64, which is giving us 0 again. So this means this is of the indeterminate form 0 over 0. We can use the L'Hopital's rule. So let's go ahead and use it. So limit as x approaches 8. So the derivative of the numerator is, so we have a square root, we have to use the chain rule, so 1/2. So remember x plus 1 to the 1/2. So square root means 1/2, so the derivative is 1/2. So the derivative of this function is 1/2 x plus 1 to the negative 1/2 times derivative of inside function is 1. So basically it is 1/2 x plus 1 to the negative 1/2, then derivative of 3 is 0. So in the denominator, the derivative is 2x minus 7. Now we can rewrite this as limit x approaches 8. So 1, so this is a negative power, so we can put it in the bottom. So we already have 1/2. So 1/2, then x plus 1 to the 1/2 means, let me write it this way. So this is 2 times square root of x plus 1, then times this quantity, which is 2x minus 7. Now if we do the substitution, we are not going to get 0 over 0 anymore, so we get 1 over, so when I put 8 here, so 2 times square root of 9 is 3, so 2 times 3 is 6, times here 8 to 16 minus 7 is that is 16 minus 7 is 9. So that gives us 9 times 6, 54. Sometimes it's hard to do this math, right? So it is 1 over 54. That is the limit of that function. Now, sometimes what happens is we might have to use the, I don't know if this is the right example I'm talking about. Yeah, I think this is the right example. Yep. So sometimes, so we can, the L'Hopital's rule is limit x approaches a f of x over g of x. So if we get 0 over 0 or infinity over infinity, then we can we can rewrite this as limit x approaches a f prime of x divided by g prime of x. But again here, after doing the first derivative of the numerator and denominator, again if we get 0 over 0 or infinity over infinity, we can keep going on with the same pattern. Okay, so we can do limit x approaches a, so we can find the second derivative, and then we can find the third derivative, and then we can keep going on until we stop getting 0 over 0 or infinity over infinity. So we can go as many times as we need, as long as we have that 0 over 0 or infinity over infinity. Okay, so let's look at this example. So if I plug in 0, So e to the 0 is 1 minus x is 0 minus 1. So we get 0 in the numerator divided by cosine of 0 is 1 minus 1 is 0. So we have 0 over 0 form. That means we can use the L'Hopital's rule. So let's go ahead and use it. So limit x approaches 0. So derivative of e to the x is e to the x minus derivative of x is 1 divided by derivative of cosine x is negative sine x minus 1 is 1. So now if I plug in 0 in the numerator, I get e to the 0, which is 1 minus 1 again 0 divided by sine of 0 is 0. So again we have 0 over 0. That means we can do another step of L'Hopital's rule. So limit x approaches 0. So derivative of e to the x is e to the x over derivative of sine x is cosine x, but we already have it that negative, so it's negative cosine x. Now if I plug in 0, I get e to the 0 is 1 minus cosine 0 is 1, so it's negative 1, which basically give us a limit of negative 1. Similarly, let's look at this example. So when I plug in x equals 0, again I get e to the 0 is 1 minus sine 0 is 0 minus 1, 0 in the numerator. The denominator, every term has x, so it is obviously 0. So now let's go ahead and use the L'Hopital's rule. So this equals limit x approaches 0, e to the x minus cosine x over 4x cubed plus 8 times 3, 24x squared plus 24x. So in the numerator, if I plug in x equals 0, so we get e to the 0, which is 1, minus cosine 0, which is 1. So 1 minus 1 is 0. Again, in the denominator, we still have x in every term, so we get 0. So that is, again, 0 over 0 form. So let's use the L'Hopital's rule again. So limit as x approaches 0, derivative of e to the x is e to the x. Now derivative of cosine x is negative sine x, but we already have a minus sign, so that becomes plus sine x divided by 12x squared. Then we have 48x plus 24. Now if we plug in 0, we get e to the 0, 1 plus sine 0 is 0. So that means 1 plus 0, 1 in the numerator divided by, in the denominator, this is 0, this is 0, we have 24. So that is the limit. Now let's evaluate this limit. So when we have infinity, okay, so when if we substitute infinity, or if x is approaching to infinity, then obviously the numerator goes to infinity, denominator goes to infinity, so we have infinity over infinity. Now let's go ahead and use the L'Hopital's rule. 6x squared plus 2x over 32x cubed. Again, still this is infinity over infinity form. That means we keep going on. Limit as x approaches infinity. So that is 12x plus 2 over 32 times 3 is 96x squared. Still we get infinity over infinity. Again, we will use the L'Hopital's rule. So that is 12 over 96 times 2 is 192x. Now, we don't have x anymore in the numerator, so this is basically 12 divided by 192 times a really large number, which is approximately infinity. So that means this becomes, which is 12 divided by a large number is approximately 0, or this approaches to 0. So that is the limit. Now let's look at this example here. So if we plug in pi over 2, okay, so tangent of pi over 2 is undefined, or is approximating infinity, and secant pi over 2 is also approximating to infinity, and this is from the left, okay, because if you look at the graph of tangent, so the graph of tangent looks like this. at pi over 2. So when we approach to pi over 2 from the left, it goes to infinity. When we approach pi over 2 from right, so it goes to negative infinity. That's why it's very important that we have that negative sign, okay? So this is infinity over infinity form. Then let's use the L'Hopital's rule. So x approaches pi over 2 from the left. So 1 derivative of 1 is the 0, derivative of tangent x is secant squared x over derivative of secant x is secant x tangent x. Now we can do some simplification here. So this one cancels out. Okay. So basically we get limit as x approaches pi over 2 from the left. So we have secant x over tangent x. So before we start substituting the value in there, let's go ahead and change this in terms of sine and cosine, and let's see what we get. So limit as x approaches pi over 2 from the left. So secant means 1 over cosine x, and then tangent means sine x over cosine x. So we have this cosine and cosine cancels out. So we basically have 1 over sine x, which means limit as x approaches pi over 2 from the left of cosecant x. And then if we do the direct substitution, we get 1. And that's the limit. So those are the 0 over 0 or infinity over infinity forms. So if we have those cases, then we can always use the L'Hopital's rule. Now there are other indeterminate forms that we are going to look at. The next one that we are going to look at is 0 times infinity and infinity minus infinity. So infinity minus infinity is not 0, and 0 times infinity is also not 0. So we really have to be careful here, okay? So what we do in those cases, so whenever we have 0 times infinity, we will have a function times another function. So in that case, what we do is we'll have a product of two functions. So in that case, what we will try to do is we'll try to change this one in terms of 0 over 0 or infinity over infinity. So if we have a product, we'll change into 0 over 0 or infinity over infinity. And it's easy to do that. So for example, if this is f of x times g of x, and if this is 0 times infinity, then what we do is we usually write it this way. So if you have f of x times g of x, we will write that as g of x divided by 1 over f of x. This is the same as if we have a times b, then we can write that as b divided by 1 over a, which is basically same as this one, okay? And then if we have infinity minus infinity, we will factor out things. We'll do some algebra and we'll factor out things, and we'll change this one in terms of 0 times infinity, and then we'll change this one in this form. So if we have 0 dot infinity, we'll change that to 0 over 0 or infinity over infinity. If we have infinity minus infinity, we'll change this one in terms of 0 times infinity, and then either in 0 over 0 or infinity over infinity form. So we have to do two steps here, okay? I'll show you examples. So if you look over here, so this is when x approaches 0 from the right. So this is 0. Natural log of x goes to negative infinity. When you approach to 0, so natural log of x goes to negative infinity. Here the negative sign really doesn't matter because we are looking at 0 times infinity or 0 times negative infinity. They are same thing. So this is of the form 0 times infinity. Okay, this is of the form 0 times infinity form. So if we have that, as I told you, so we'll change that into either 0 over 0 or infinity over infinity. And for that, so if we have a times b, we either write b divided by 1 over a or a divided by 1 over b, depending on what function we want. Okay, so now here we can rewrite this as a limit x approaches 0 from the right, natural log of x, and we divide by the reciprocal of 1 over x. And basically it's the same thing. Algebraically it's same, because when you divide by 1 over x, So when you have this one, it's basically you are going to do natural log of x times the reciprocal of this one, which is x. That's what we have, x times natural log of x. It's not really going to change any value, but it's going to change that form. Okay, so now if you look over here, as x approaches 0, natural log of x, that is infinity, divided by 1 divided by a number which is close to 0, means a really small number. So any finite number divided by a really small positive number is infinity. So we have infinity over infinity form. That means now we can use the L'Hopital's rule. So limit as x approaches 0 from the right. So derivative of the numerator, which is 1 over x, divided by derivative of denominator, which is negative 1 over x squared. And then if we simplify that, we get limit as x approaches 0 from the right. So this is negative x. Now if we do the direct substitution, we just get 0, and that's the limit. Let's look at another example. Now, if we do the direct substitution, we get x means infinity minus infinity. So remember, if we have this form, infinity minus infinity, first we'll change this one in the form 0 times infinity, and then we'll change this in the form either 0 over 0 or infinity over infinity. So that is the process. Okay, those are the steps that we are going to use. So in order to change this into 0 times infinity, we need to have two factors. We need to factor things out. Okay, so we have x here, so we need to factor out x from here as well so that we can factor everything out. So let's see what we can do. So limit as x approaches infinity, x minus, so let's do this. Okay, let's factor out x squared here. So we have 1 plus 1 over x squared. If I factor out x squared from here, okay? Now, if I bring that x squared out of the root, then we get x minus x square root of 1 plus 1 over x squared. Now I have x here and here, so that means I can factor that out. So limit as x approaches infinity. So this was, let me write it down. Okay, I forgot to write that. So it's infinity minus infinity form. So we need to denote that. Okay. So now if I factor out x, then I get 1 minus the square root of 1 plus 1 over x squared. And now this is in that form. So it's in the product. Let's go ahead and check it. Okay. So if I plug in infinity, so x is infinity times, so 1 minus, if I plug in infinity here, this is 1 over infinity is 0. So you have a square root of 1. So 1 minus 1 is 0. So it is in the form infinity times 0, or which is same as saying 0 times infinity. So that means now it is in this product form, so we can change either in 0 over 0 or infinity over infinity form. So what I'm going to do is, remember it's the same process, okay? So I'm going to write 1 minus square root of 1 plus 1 over x squared divided by 1 over x. Now this is in the form 0 over 0. Now if you check here, okay, so when I plug in infinity, this goes to 0. So I have 1 minus 1, 0 in the numerator. 1 divided by a very large number is 0. So it's in the form 0 over 0. That means we can use the L'Hopital's rule now. So let's go ahead and find the derivative. So limit as x approaches infinity, derivative of 1 is 0. So we have minus, so this is a square root. So remember the square root means to the power 1/2. So we have to use the chain rule. So 1/2 times, and we have 1 plus 1 over x squared to the negative 1/2 times the derivative of inside function, which is 1 over x squared. So the derivative of 1 over x squared is negative 2 over x cubed divided by negative 1 over x squared. So that's the derivative of 1 over x. Now let's see what we can do here, what simplification we can do. Okay, so now these two, let me cancel things here. So these two and these two cancels out, okay, and then this negative and negative, when you multiply, you get positive. So we just have one negative here. So let me go ahead and write this over here. So this equals limit as x approaches infinity. So in the numerator, what we have is, so this is a negative power, so we'll put that in the denominator. So what we have is so this is 1 over x squared, so that goes in the numerator. So negative x squared divided by x cubed. So this one we can write as a square root of 1 plus 1 over x squared. Okay, now this x squared cancels out with this one. Now we have limit as x approaches infinity 1 over x times square root of 1 plus 1 over x squared. So now let's see what we get. So if we try to put infinity, or if we try to see the limit means when it approaches to infinity. So this is infinity, this is 0. So 1 plus 0 is 1. So in the denominator, we have this infinity. So 1 over infinity is 0. So this limit is 0. Now, there are other several indeterminate forms. So the next indeterminate form are 0 to the 0, infinity to the 0, and 1 to the infinity. So 1 to the infinity is not 1. Infinity to the 0 is not 0, not 1. Okay, so usually we say a raised to 0 is 1, except a is not equal to 0. And then also a is when a is not equal to infinity, because we're talking about the real numbers. So these are some of the indeterminate forms. So how do we take care of this one? So when you're finding the limit, if you get 0 to the 0, or infinity to the 0, or 1 to the infinity, so we do very similar process for all these three types. What we do is we'll take natural log on both sides. Remember when we did derivative, if we have variable raised to variable, then in that case we take natural log on both sides. So this is very similar when we have a function raised to function. Okay, we will take the natural log on both sides, and then after that we will either get 0 times infinity, or we'll get infinity minus one of those forms, and we'll just follow what we did in the previous example. So let's go ahead and look at an example. So this is x to the sine x. So if I plug in 0, I get 0 to the sine of 0 is 0. So we get 0 to the 0 form. So as I told you earlier, in that case, we are going to take natural log on both sides. So this is how I'm going to rewrite this. Okay, so I'm going to write L equals, L means the limit. Okay, so this limit as x approaches 0 from the right, x to the sine x. Now take natural log on both sides. So we get natural log of L equals natural log of limit x approaches 0 from the right, x to the sine x. Now we can put that limit inside, so we can write limit L equals, natural log of L equals limit x approaches 0 from the right of natural log of x to the sine x. Okay, now natural log of L equals, so now by using the rule of log, remember if we have log base a of x to the k, we can bring that power out to the front. So that's what we are going to do here. So we can bring that sine x to the front. So limit x approaches 0 from the right, sine x natural log of x. Now if you check, this is 0 times infinity, because when x approaches 0, sine of 0 is 0, and then natural log of when x approaches 0 from the right is infinity. So this is in that form. That means we have to change this one in the form uh, 0 over infinity, or infinity over infinity. Remember, so what we can do here is we can divide this one by 1 over sine x. So it's a times b equals b divided by 1 over a. Okay, so when we do that, we get 1 over sine x, which means cosecant x. So we can rewrite this as natural log of L equals limit x approaches 0 from the right, natural log of x over 1 over sine x means cosecant x. So I'll just write it as cosecant x. Now, this is in the form infinity over infinity. Okay, so we can use the L'Hopital's rule. So limit x approaches 0 from the right. So derivative of natural log of x is 1 over x. Derivative of cosecant x is cosecant x times cotangent x. Okay, now let's see what we get. So natural log of L equals limit as x approaches 0 from the right. So 1 over x. So here we have cosecant. So we have cosecant times cotangent, which means 1 over sine x times cosine x over sine x. So this is cosine x over sine squared x in the denominator. So we have 1 over x. Okay, so we can write this one as 1 over x divided by cosine x over sine squared x. And that is going to give us, so let me rewrite here, okay? So let's take it over here. So this equals, natural log of L equals a limit as x approaches 0 from the right. So this becomes, so we are dividing by cosine x over sine squared x. So this becomes sine squared x, okay, divided by x cosine x. Now if I plug in 0, still I get 0 over 0 form. So that means natural log of L equals limit x approaches 0 from the right. So derivative of sine squared x is 2 sine x times cosine x divided by derivative of x times cosine x is we have to use the product rule. So first function derivative of second plus second function derivative of first is just 1. Now if we plug in 0, in the numerator, we obviously get 0 because we have sine x. Here we get 0, but here we get 1. So we get 0 over 1, which means natural log of L equals 0. Our goal is to find L because that's what the limit we are looking at. So natural log of L equals 0 means L equals e to the 0, and that gives us L equals 1. So that means limit as x approaches 0 from the right, x to the sine x equals 1. Okay, so let's look at one more example. So again, this is same as the previous one. We have a function raised to a function. So in that case, again, we are going to take the natural log. So this is, so if you check, so 3 divided by infinity is 0, so 1 raised to infinity. That is the form that we have here. So let's write L equals limit x approaches infinity, 1 plus 3 over x to the x. Then we take natural log on both sides, so we get natural log of L equals, so again we can put natural log inside, so I'm going to skip that step as we saw that in the previous examples. I can write natural log of 1 plus 3 over x to the x. And then we can bring that power down, so this becomes natural log of L equals limit x approaches infinity, x times natural log of 1 plus 3 over x. Now if you look over here, this is of the form, so infinity times 0, because when you plug in infinity here, 3 over infinity is 0, so natural log of 1 is 0, and then we have infinity, so which is same as saying 0 times infinity form. Now for that, again, we have a product, so it's the same process. We are going to change this to a quotient, so natural log of 1 plus 3 over x, and then we divide by 1 over x. And if we put infinity, so we get 0 over 0 form. Okay, that means we can use the L'Hopital rule here. So L'Hopital's rule says that we find the derivative of the numerator and denominator. So x approaches infinity. So derivative of natural log of x is 1 over x. But we have to use the chain rule here. So 1 over 1 plus 3 over x, because it's 1 over whatever that quantity, times derivative of this function. So derivative of 1 is 0, derivative of 3 over x is negative 3 over x squared. Everything divided by derivative of 1 over x is negative 1 over x squared. So if you look carefully here, so this negative cancels out, this x squared and x squared cancels out. So this basically becomes natural log of L equals limit x approaches infinity 3 over 1 plus 3 over x. Now if we take the limit, this one is going to become, so let me write it here, okay? So natural log of L equals, so when x approaches infinity, this quantity down here, this quantity goes to 0. So it is 3 divided by 1, which is 3. And then if you solve for L, you get L equals e to the third. That means the limit as x approaches infinity, 1 plus 3 over x to the x equals e to the third. Now from here, I'll give you a general case, okay? So if we ever have something, so just looking over here, okay, there's a pattern for this one. So if we have something like this, limit as x approaches infinity, 1 plus a constant, let's say c, over x to the x. If we have that, this is always e to the whatever that constant c. So if you look over here, the constant is 3. So it is e to the third. If this was 4 instead of 3, then that would be e to the fourth, and so on. So we'll just stop here for this video. I think this video is a little bit longer because it is a lot of work with the L'Hopital's rule. So yeah, I'll see you again in the next video. Have a great day.